All right, one of our first applications of the second fundamental theorem of calculus is if we define the natural log of x to be the definite integral between 1 and x of 1 over t dt. If we take the derivative of the natural log of x, it's going to give us 1 over x by the second fundamental theorem of calculus. So let's do a couple of examples that deal with this. So let's say our function f of x is equal to 1, or I'm sorry, it's going to be ln of x plus 2, and we're going to take the derivative of that. And it's not quite the same thing, it's not ln x, it's ln of x plus 2, so we're going to have to use the chain rule when we take the derivative. Well, the inside function is just x plus 2, and the derivative of that is just 1. So when I take the derivative, it's just going to be 1 over the argument times the derivative of the argument, which is just 1, so we won't even put the times 1 there. So nice, straightforward. The derivative of ln x plus 2 is 1 over x plus 2. Okay. Now if we look at another function, ln of x squared over x plus 5. This would be kind of harder to do if we didn't use some properties we have with logarithms. If you're not real familiar with the product, the quotient, and the power rules for logarithms, different from the derivative rules, I do have some videos that would be called expanding logarithms, would probably be what the name is, and they would be on my playlist called Unit 3, or maybe it's Unit 4. It's either on Unit 3 or Unit 4 where I have expanding logs. So if we expand the logs, and I got a quotient here, so that would mean I'm going to have subtraction. So I'd have ln of x squared minus ln of x plus 5, and then I'm going to use the power rule, which would also bring down that 2. So those are just properties of logarithms that you would have seen in both college algebra and pre-calculus. Okay, so that becomes 2 ln x minus ln of x plus 5, and then it's real straightforward and nice and easy to take the derivative. Okay, so we got that constant of 2 out in front, and derivative of ln x is 1 over x, minus the derivative of ln of something is going to be 1 over that something times the derivative of that something. And that something's derivative, the derivative of x plus 5 is just 1. So that's our derivative. Nice, straight and forward. We didn't have to use the quotient rule for derivatives or anything like that. So those properties of logarithms are going to make this process a little bit nicer. Okay, so what if we do something a little bit more crazy where, again, it's not real crazy unless we don't have our properties of logarithms down real well. Okay, so here's what I got going on here. I got a fifth root, and that's the same thing as a 1/5 power. Then I got a quotient there, which is going to have a subtraction of the ln of the numerator minus the ln of the denominator. And that's just using the quotient rule for natural log. Natural log is the same thing as a logarithm. Follows all the rules. Okay, so that 1/5 is going to hang out in front. That's the fifth root. ln of the numerator minus ln of the denominator. So when I take the derivative, the 1/5 is just going to be hanging out in front. And then it's going to be 1 over x plus 3 times the derivative of x plus 3, which is just 1, so it doesn't change anything, minus 1 over x minus 4 times the derivative of x minus 4, which is just 1, so that doesn't change anything. And there you are. I mean, there's other things you can do. You can distribute the 1/5 through, you can find common denominator, all that kind of stuff, but that's as far as I would like to take it. Okay, we'll do a couple more examples here. And one of the applications of the log is using it in log differentiation. And we're going to look at something that would be kind of tedious to do if we want to take the derivative of this particular function. I have the fifth power there, or not fifth power, but 1/5 power, so I'd have to use the power rule. And then I would have to use the chain rule, which would require me to take the derivative of all the inside stuff. Well, taking the derivative of all the inside stuff would have me use the the product rule. And so that's a lot of work. And so what we're going to do is we're going to use the fact that the natural log is a nice function, and we're going to assume that this is all positive, so and non-zero, so that it's in the domain of the natural log. And so what we'll do is we'll take the natural log of both sides, and the natural log has those nice properties which will allow us to break this fairly complicated argument up into some pieces. So again, we got the fifth root, which is a 1/5 power, so we'll use the power rule to bring that forward. And then we'll have the ln of an x squared, and then plus ln of an x minus 1, and then we'll have plus an ln of an x plus 4, and that's using our product rule for logarithms. Okay, and what that's going to do for us is it's just going to make this problem a lot easier. And also we'll use the power rule to bring that 2 down in front on the x squared. So that's what's going on here. Again, those properties are illustrated on the video that I have. Okay, so we're just using those properties of logarithms to make this problem that would be a lot of work a lot simpler. Okay. And we do have to use a little bit of implicit differentiation, because we assume that y is a function of x, and in fact it is a function of x. It's explicitly defined as a function of x. So when I take a derivative of y with respect to x, I'm going to have to use the chain rule. So the derivative of ln y is going to be 1 over y times y prime. Then we'll take the derivative of all the stuff inside, which is just going to give me 1 over the arguments. Okay? And then one last thing we're going to do is we're going to multiply both sides by y, so that we'll just have y prime by itself. And instead of writing y, I'm going to write what y is equal to. And what y was equal to was the fifth root of all that junk there. So y prime is going to be the fifth root of all that junk. And then it was divided by 5. And then times the 2 over x plus 1 over x minus 1. And plus 1 over x plus 4. And that is my derivative, again made so much nicer with using properties of logarithms.